Okay, welcome back. What we talked about last time was trying to understand functions in terms of various ways of picturing them. Now, what we will do today is to talk about functions from R2 to R2. So, R2 is the plane to the plane, and let us just do this by examples. So, I am going to write out a sequence of examples. So, let us take first example to be the function f of x y equals x plus 1 comma y plus 2. Okay. Now, let us try and picture this function, try and understand what it does. So, typically how does one want to understand functions from R2 to R2? So, here are the various ways of thinking about R2. What are various subsets of R2. So, R2 has points. So, each of this is a point in R2. The other subsets of R2 of interest might be say lines or more general curves. So, for instance, I could think of lines, or maybe I could think of circles, or maybe even more general curves like parabolas or ellipses, or just even more arbitrary curves. So, I could look at lines, I could look at circles. So, these points are sort of what we often call 0-dimensional objects. Lines are just 1-dimensional, circles are also just 1-dimensional, the plane itself is 2-dimensional, and we could also look at regions in the plane. So, by a region we mean sort of a 2-dimensional thing. So, let us say you could take the region that is inside a circle. So, this disk is often what you would call a region in R2. Of course, a region need not have such a nice shape, it could be a bit more arbitrary shaped region. So, here are various subsets of R2, and one way of trying to understand a function f is to see what it does to each of these kinds of things. Okay. So, at the very basic level, what you are really given is how a function acts on a point x comma y to produce another point. Okay. So, let us first think of what this function does to a typical point in R2. So, if I have the point x comma y, here is the point, it is 1 unit to the right and 2 units above point x y. Okay. So, what this function does is really the following: it takes this point x comma y and moves it or maps it to this point here. Okay. And it sort of does this uniformly, it does this to every single point on the plane, it takes it and moves it by the same distance and the same direction. So, it takes this point, it would similarly move it parallelly, this guy would also move parallelly. Okay. So, sometimes this map here is called a translation, and it is a translation by the vector 1 comma 2 if you wish. Okay. So, it translates everything by that amount, 1 unit to the right and 2 units above. So, now let us ask so this is actually a very simple sort of map. What it does to everything is pretty much has the same description. What does this map do to a line, for instance? So, suppose I have a line on the plane, asking what it does to the line is like asking what does it do to all the points of this line. So, every point of this line moves by the same amount, right. So, all points of this line slide up to those points, and so this line here, let us call it L, maps to a parallel line. Okay. So, this is L dash. So, what it does is, well, it sort of also translates the line L by the same amount 1 comma 2. So, lines map to parallel lines. So, line L, what does it go to under the function f? It goes to a parallel line. L dash, which is shifted by the amount 1 comma 2. Okay. And well, you can think of the same thing. If you have a circle, the same thing will happen. It will go to a shifted circle, something shifted by the amount 1 comma 2, or more generally if I have a region, the same thing. So if I have some sort of region on the plane, then what does this function do to this region? So you look at what it does to all points of this region. All points move by that amount. So of course what this function ends up doing is really the same thing. So it moves this region up by the same amount. Okay. So this is the new region R dash, the original region R. So R maps to R dash under this function f, and what's R dash? It's just a shift. It's just R shifted by 1 2. That's basically R dash. Okay, so a translation is very easy to describe. It just does sort of the same thing everywhere. It just moves everything by some fixed amount. Okay, so let's look at the second example. If I have a function defined as follows: x comma y equals x comma minus y. Okay. So again, first let's try and understand what this function does to points. So if I have a point x comma y on the plane, what this function does is, well, it keeps the x coordinate the same, but maps it to the point x comma minus y. Okay. So the point, let's call it a, maps to the point a dash under this function. So a goes to a dash, and what's a dash? Well, one way of describing a dash is to say it is just a reflection of this point a about the x axis. So observe, a dash is just the reflection of a about the x axis. Okay. So this map f here, it's again very easy to describe. It just does a simple reflection about the x axis. Okay. So again, similarly, if you have say a one dimensional subset, say I have a line in R2 and I want to know how does this function transform this line, what does it do to this line. So I just see what it does to each point of this line. Well, similarly, it just maps, it reflects each point of this line about the x axis. So it just gives me a line, it gives me the reflected line. So this is what the function would do. It's just a mirror image. So this is a line L maps to the line L dash. Okay. And observe, of course, these lines will intersect somewhere on the x axis. Okay. So that's the picture for what it does to lines. Now, and similarly, if you want to do regions and so on, it's not much harder. But here's often an important and illuminating aspect that helps us understand some of these functions. That's the notion of an invariant figure. Okay. So what is an invariant figure? We will call a figure, by a figure I mean it in the most general sense, could be points, lines, curves, regions and so on. An invariant figure is one which is which does not move under the function in some sense, which is mapped to itself under the function. So what's an invariant figure? I will call a figure f, maybe let's not call it f, let's call it okay, an invariant figure is the following. You say that a figure k is invariant under f if when you apply f to that figure, which means you apply f to each point of that figure, what you get back is that same figure that you started with. Okay, in other words, it somehow maps that figure onto itself. So let us do some examples to get a better sense of what this does. Let us do it for the case of the reflection about the x axis. So I will come back to translation. So if I take the reflection about the x axis, observe that any figure that is symmetrical about the x axis. So for instance, if I take say a rectangular figure like this which is symmetric about the x axis, say if I take this region for instance to be k, then when I reflect it about the x axis, what I get back is the same region, because the top half will map to the bottom half and the bottom half maps back to the top half. So observe this k is invariant for the reflection, right, for under the reflection about the x axis. Similarly, pretty much any figure that is symmetrical about the x axis will be invariant. Now let us think about translation. So here is the first question, is there anything at all that is invariant under the translation, okay, because it seems as if the translation moves everything, right, it seems to move everything in one uniform fashion. So no matter which region you tend to think of anywhere, it seems as if the translation will move it. But observe a line for instance. So if you took so imagine the following, you take a line L which passes through the point 1 comma 2, okay, and through the origin. Now imagine what the translation will do to this line. Well, what it will do is to move every point on this line by 1 comma 2. So the point 1 2 moves to the point 2 4, 2 4 will move to the point maybe 3 5 or 3 6 and so on. But pretty much no matter which point you take on the line, what you will get is another point on the same line, okay. So the line sort of slides up by 1 comma 2. So here is an example of a figure. So if you take k here to be this line, or in fact any line parallel to this one, then you apply the translation, you will find that k in fact does not change, k is invariant under the translation. Okay, so good, we have talked about translations and we have talked about reflections. So here is another one. f of x comma y equals minus y comma x. So let us try and see what this does, firstly to points. So if you imagine a point somewhere here, let us call it x comma y, minus y comma x. So minus y is, that is the new x coordinate, and then x, so that is this. And if you sort of try and compute angles and so on, you will find exactly this is a 90-degree angle. Okay, so what does this map to? Well, it takes every point and rotates it counterclockwise by a 90-degree angle. So this is nothing but the anticlockwise rotation by a 90-degree angle. So that is what it does to each point on the plane. So of course it is easy to see what it does to other things. For instance, say the x axis, the line which is the x axis will of course map to the y axis because it is a 90-degree rotation. The y axis similarly will map back to the x axis, or in general, so let us just say this. So the x axis under this map f will map to the y axis. In fact, the y axis also maps to the x axis under this map, and in general any line will just map to the line that is perpendicular to it. If you take a line through the origin, you rotate it 90 degrees, so it maps to a perpendicular line, L will map to L prime. So that is what happens to lines. Region, similarly you imagine a region anywhere on the plane, and just what you get is the rotated region. But again what is interesting here is to look for invariant figures. So does rotation have invariant figures at all? So here is one obvious figure, which is just a circle about the origin. If I take a circle about the origin and imagine what happens when you rotate it by a 90 degree angle, well you just get back the same circle, right. So a circle through the origin is in fact invariant under this transformation, but of course one can even find other such invariant figures, because all you are doing is just a 90 degree rotation. So imagine placing a square in this fashion, it is not a very good figure. So imagine this is a square, and you sort of look at what happens when you rotate this by a 90 degree angle. All that will happen is that this vertex will now coincide with the next one, that will coincide with the next one, and so on. So here is an example of a figure which is invariant under a 90 degree rotation. So a circle is special in the sense that it is in fact invariant under rotation by any angle, not just by 90 degrees. So this figure is very special, it is invariant if you rotate it by 90 degrees, 180 degrees or 270 degrees, but not by other angles. If you rotate by say a 45 degree angle, this will not give you back the same figure, whereas a circle is sort of perfectly invariant under every possible rotation. Okay, so we have looked at three functions: the translation, and they have the following interesting property. So for now what have I done? I have given you examples of three functions: the translation function, the reflection about the x axis, the rotation through 90 degrees. So we have looked at three such functions, and one interesting aspect of all of them is the following, that they all map a region R to a congruent region R dash. So if R is any region in R2 and you take any one of these three fellows, translation, reflection or rotation, what does it do to R? Okay, it maps it to R prime. So this can be a translation, reflection, rotation. Any one of these three acting on the region R will give you a congruent region R prime. Okay, what does congruence mean? So where R prime is congruent to R. Okay, congruent, remember, means the following, that you can superimpose R on R prime in such a way that they coincide exactly. Okay, so that is what congruence means. So observe, if I had, say imagine you have a region. So of course if you translate it by some amount, clearly it is the same region, right. So the translated region R prime is, it is clear it is congruent to R, it is just a copy of R that is just physically moved by that amount. A reflection, well, in order to make these two things coincide, so if I have let us say, so I have a figure like this, say that is my region R, and if I look at what happens to it under the reflection, well, this will map here, the this point and this point will map to a point here and a point there. So maybe we will just draw it a little better. So that is the reflection about the x axis of this original figure R, but again it is clear they are congruent. In order to make them superimpose, you just need to align the correct sides together. So for instance this side here has to be aligned with this hypotenuse here, and similarly, so I am imagining this is a right triangle. Similarly, this horizontal side aligns with this, and likewise for the third. And similarly for a rotation, when you rotate, of course the entire figure moves by some amount, but you need to reorient it, you need to sort of rotate it back in order to make them align with each other. Okay. So it is again sort of visually clear that rotations also give rise to congruent regions. If you take a region R, it maps it to a congruent region R prime. So in particular, these have the property that they do not change areas of regions. So what is the property of translation, reflection and rotation? Well, translation, reflection, rotations, they preserve areas. So if in R, it gives me back another region of the same area. In fact, it gives me back a region which is congruent. In fact, it preserves lengths, it preserves angles. Okay. So it preserves all of these. So what does it mean to preserve lengths and angles? Well, if I have a line segment somewhere on the plane, and say let us say this is segment, and if I see what happens to it under a translation, I get back another line segment of the same length. Likewise, if I reflect it or I rotate it, the length of the line segment that I get does not change. I always get it, maybe it's oriented slightly differently, but I get the same thing. That is what length preservation means. Angle preservation means, imagine I have two line segments, and now I take this figure here and I say translate it, or I reflect it, or I rotate it. Now doing any of these three will never change the angle between the resulting line segments. Okay. It cannot deform the angle between them, it can only move this entire figure somewhere else. Okay. So this property of translations, reflections and rotations is sometimes encapsulated by saying that these are all rigid motions. Okay. So because of these properties that they do not really change either lengths or angles, we often say that translations, reflections and rotations are often called rigid motions of the plane. Okay. So by rigid motions we mean you just move, think of moving the entire plane in some way as sort of like a rigid body. Imagine the whole thing is made out of metal or something which cannot be deformed, then you sort of move the whole thing, or maybe you reflect, you rotate. These operations do not really deform, they do not change lengths for instance, or they do not shrink, they do not sort of make angles smaller. So that is what rigid really is supposed to bring to mind. Now what we will do next during the next lecture is to also look at other examples. So of course these are not the only interesting examples. What about maps which deform? Okay. So this is to be contrasted with maps which are sometimes called deformations. They deform lengths or angles or areas, so sometimes also called, there are many different kinds of these. So I am just using this as a loose term to mean something that does not act in a rigid fashion. Okay. So we will look at examples of these. So there are things called dilations, and then there are more general linear transformations. Okay. But that will be for next time.